The angle between two vectors is the angle theta that is between the vectors when they share the same initial point. That angle is also required to be somewhere in between 0 and 180 degrees. And if we wanted to calculate the angle between the two vectors u and v, now remember u and v with bold print is indicating a vector. It's better to put vector hats on them if we're handwriting those so that it's clear that what we're talking about is a vector. If we wanted to calculate the angle between the two vectors, the formula for doing so is this. The cosine of the angle in between is equal to the dot product of u and v divided by the product of their magnitudes. And we are in this video going to prove that. So let's just pop these two vectors, actually three vectors, down onto a Cartesian plane. And then notice that we have the vector u minus v as the other side of this triangle. If we were to think about vector addition, if we were to take vector v, which comes from here to here, and add that to vector u minus v, right? This is the correct way to add two vectors, is to have the initial point of the second vector on top of the terminal point of the first. So notice that v added to the vector u minus v would be equal to the vector u, right? Because vector v and vector negative v would cancel each other out, and then we would end up with the resultant vector being vector u. So that's just a quick way of convincing you that this vector here is actually u minus v. So for this proof, we're going to use the law of cosines from trigonometry, which says that if I look at this side here, u minus v, and we want to talk about that as a length. So let's look at the magnitude of the vector u minus v, and we square that side. It's going to be equal to the sum of the squares of these two sides, right? So if I want to look at their length, we would need its magnitude, so that's going to be mag u square that plus mag v square that. It looks a little like the Pythagorean theorem, but then we minus 2 times the magnitude of u times the magnitude of v, and we multiply that by the cosine of the angle that was opposite the side that we started with. This is the law of cosines from trigonometry. Now, from some previous properties that we've already discussed, we saw that a dot itself was equal to the magnitude of a squared, which is going to enable us to expand on these items here. So let's do that. We have mag u minus v quantity squared, so let's rewrite that as u minus v dot itself. And we'll carry that on down the line, expressing these mag squareds as dot products, applying that property. And these two magnitudes are going to have to stay, of course, because they're not mag squareds. And now let's look at another property that we've already discussed, which is that if I take two vectors, add them together, and then dot product with a third, the resultant would be essentially like distributing that dot product into the parentheses and getting a dot b, add that to a dot c, and how we can think about this is essentially that the dot product is distributive, or that we enjoy the distributive property. Now, what that tells me is that I can use the distributive property to carry out this multiplication, which the distributive property, when I'm looking at binomials, if you will, is essentially the foiling that we've seen from algebra. Foiling is using the distributive property with binomials. So we're going to FOIL this, and we'll end up with u dot u, that first multiplication, or that first dot product, minus u dot v minus v dot u plus v dot v. And then we just copy paste the other side. Now remember, a dot product is a scalar quantity, right? So that when we are getting all these dot products, this is a scalar number. It might as well be a 4 or something like that. But I get that same scalar quantity over on the right-hand side of my equal sign, so these two scalar quantities are going to cancel each other out. I could essentially think about subtracting it from both sides. Here we have another scalar quantity that appears on both sides of the equal sign, so we cancel that out. And now let's use one more property of the dot product, which is that it is commutative, which means that if I have two vectors dot producted in one direction, that's going to give me the same scalar quantity as if I were to dot product in the other direction, which tells me that this scalar quantity and this scalar quantity are the same, so I might as well write it as having two of those scalars, so we'll say that's minus 2 of the dot products u dot v, and then on the other side all that remains is negative 2 times mag u times mag v times the cosine of theta. Notice that I'm being really good about putting my vector hats on top of all of my vectors. That's essential that we know what's a vector, because sometimes variables are scalars, so we need to differentiate between those. Now, the next step, because we're headed towards proving this theorem, is that we're going to want to try to isolate cosine theta. So the first thing let's do is divide off that negative 2, right? We'll get rid of that scalar quantity there. So that cancels. And in order to isolate the cosine, we would also divide both sides by mag u mag v. So we would end up with cosine by itself on one side, and then u dot v all by itself in the numerator, and in the denominator we would have mag u times mag v, and that is what we were trying to prove. So we'll stop with the proof here. Now let's notice a couple of other things that will result from this theorem. Is that if we have the dot product of two vectors that gives us 0, then we're going to have the cosine of the angle in between the two vectors must be 0. And remember, since the angle in between the two vectors had to be somewhere in between 0 and 180 degrees, there's really only one option for that angle. And the only angle in between 0 and 180 that has a cosine of 0 is 90 degrees, right? So here is our ordered pair that would be on the outside of the unit circle, and this angle inside here would have to be 90 degrees, which means that if the two vectors have a dot product that is equal to 0, we can safely assume that those two vectors are perpendicular to each other. And that's because the angle in between those two vectors would have to be 90 degrees. So that gives us a nice little shortcut. We wouldn't actually have to calculate the angle. We could just say, if this happens, then we know that those two angles are perpendicular. Now, another thing to notice is that if we do follow through with the calculation, trying to find the angle between the two vectors, and we get that the angle is either 0 degrees or the angle is 180 degrees, that is an indicator that u and v are what we call parallel to each other. So if we calculate the angle in between those two vectors, it must be that vector u and vector v either are in the exact same direction, which would mean that if I slide it so that their initial points are on top of each other, it would look like this, and in this case the angle in between would be 0. There's the angle in between two vectors is measured when their initial points are on top of each other, and if they're in the exact same direction, the angle between is 0, which means that they're parallel. The other situation would be that if I had vector v coming off in some direction and the vector u being in the exact opposite direction, once I slide it to where their ordered pairs are on top of each other, we would see here that the angle in between the two vectors is 180 degrees. But also, this is another situation where we would say that the two vectors are parallel to each other. Either headed in the exact same direction or in the exact opposite direction, those two vectors are parallel.